Thank you, Chiara, for the introduction. Good morning, everyone, and thank you for joining us for Climate Coffee. I'm Giulia Bonino, Junior Scientist at CNCC in Bologna, and today I'll be presenting a study we recently published in Nature Geoscience in collaboration with Ronald McAdam, with whom I share the first authorship, and with Panos Athanasiasis, Leone Cavicchia, Regina Rodriguez, Enrico Scoccimarro, Stefano Tibaldi, and Simona Masina. The title is Mediterranean Summer Marine Heatwaves Triggered by Weaker Winds Under Subtropical Ridges. Why this slide is not okay. Okay, let me start with some context on why this matters. The Mediterranean Sea is one of the most climate vulnerable regions on the planet. It has been identified as a climate change hotspot. And when we talk about warming, the numbers are quite impressive. The Mediterranean is warming at roughly twice the global average rate. Indeed, while global mean surface temperature rising approximately 0.1, 0.2 degree per decade, as we can see from the left figure, the Mediterranean has been raised closer to 0.3, 0.4 degrees Celsius per decade, as we can see from the right panels. Of course, this background warming has a direct consequences. For example, it rises the baseline from which the marine heat waves are measured. Making the extreme SST anomalies more frequent, more intense, and also longer lasting. So basically what is happening is that the marine heat waves have already become a feature of the Mediterranean summer, and this trend is only going to be intensified. So understanding what drives them is one of the major scientific questions, and as also is a practical question that we have to answer in order to make action. So to make this concrete, here in this slide is what a Mediterranean marine heat wave summer actually looks like. This map shows a snapshot of SST anomaly for the summer, exactly in June of 2025. And as we can see from these maps, we are talking about anomalies up to 6 degrees Celsius above the climatological baseline over the large portion of the Mediterranean Sea. And 6 degrees Celsius is quite a lot. So the impacts are broad and well documented. For example, these kind of heat waves leads to mass mortality events in the benthic system for the corals, for example, in the panel A. We have also some impact on the economics and fishery, the economics of the fishing and tourism as the panel C. And these events also interact with atmospheric extreme, like the tornado, as you can see here over the Liguria. So they boot the storms. But I want to focus your attention on something like more immediate. These events are not anymore tails, as I said before. They are not happening now once a century, but they starting to become a new normal. So that's why we start to study what is really causing this event. But what do we already know about drivers of the marine heat waves in the Mediterranean? So from previous work by the NAXA in the left panel and Simon in the right panel, they have established two important things. First, at local scale by the NAXA et al., air sea fluxes are the primary drivers of SST warming during the marine heatwave onset in roughly half of the events. Indeed, if we look to the plot bars on the left, you can see that the ratio of the QNet to SST tendency is greater than 0 for almost all the events. Second, here from the right panel, from a more synoptic scale, this anomalously warm summer tends to concur with high pressure systems. So now, these two papers basically are saying the local scale driver, and they are also identifying a synoptic scale driver. But they didn't explain the link between these two processes. So we asked ourselves which large scale atmospheric pattern is actually responsible of this anomaly, and what is the physical chain from the atmosphere to the ocean that is driving this event. So those are the questions that we answer in our paper. To answer them, we took a multi-event, multi-decadal approach. Indeed, we examined 123 summer macro events across the Mediterranean from 1982 to 2022. This dataset is based on a previous dataset that I built during my ESA fellowship. And here you have the paper as well, where you can find the dataset. So this dataset is built from the ESA CCI SST satellite product that is a really high resolution one, 0.05 degree of horizontal resolution. Then what we did is we detected marine heatwave at each grid point against a moving baseline climatology, but we used the OBDAY definition, and we also detrended the time series using a decomposition method in order to remove either the local trend and the seasonal variability. Then, when we had all the marine heatwave there are in each grid point, we spatially connected these marine heat waves, aggregating them in order to have macro events that are connected. So basically, we passed from a pixel-based dataset to an event-based dataset. After that, when we had this data set, we then apply hierarchical clustering algorithm based on cosine distances to identify typical spatial pattern of our marine heat waves. This gives us three clusters. The Western Mediterranean cluster, the WMED, with 26 events. The Central Mediterranean, the CMED, with 12 events, and the Eastern Mediterranean, the EMED, with 14 events. Then from the atmospheric side, so this is basically our marine heat waves dataset. For the atmospheric side, we use ERA 5, and we we take a look to the surface heat fluxes, wind, and 500 hectopascal geopotential high. Okay. So let's go into the result. This slide shows two things. On the top row, the SST intensity of the three marine heat wave clusters. And as you can see, the anomaly reaching 3 degrees Celsius during onset for example, in the Gulf of Lion and the Ligurian Sea. And on the bottom row, the composite of the Zeta 500 anomalies in the ERA 5 during the 5 days onset period preceding the marine heat waves peak. We define the peak of our macro events as the day in which the macro event reach its maximum area. As I said before, we are not just examining the pixel-based marine heat waves, but they are macro events, so they are aggregation of points. So they start with probably with just a few of events, and then they grow. When they reach the maximum area, this is our peak day, and we are always examining the condition prior of this peak. From the picture, the figure below, so the signal, you can see the signal is consistent and clear across all of the three clusters. And as Simone et al. Show before, these macro events are associated with anticyclonic circulation. So basically we have positive zeta-500 anomalies in red, and then that are located directly above the marine heatwave region, so where we have the maximum of the intensity, and this positive anomaly are surrounded by cyclonic center on the either side, forming a wave train pattern that propagates across the Mediterranean basin. This pattern shifts longitudinally from west to east, here, following the location of each cluster. So what we can understand from this is that we have a strong hint that we are not dealing with a fixed synoptic structure, but something that is more flexible, that is moving. But our question was, so what's exactly are these atmospheric anticyclonic system? Okay, so in the literature, there is a tendency to automatically attribute this kind of pattern, anticyclonic pattern, to atmospheric blocking, and this is sometimes incorrectly. So we instead consider two indices, or two, let's say, synoptic patterns. So we consider subtropical ridges, STRs, which are extension of the subtropical high pressure belt beyond its zonal mean latitude. So they are meanders of the westerly flow that redirect atmospheric circulation poleward over the Mediterranean region. And then we also consider blocks that are similar to STR, but so they are also redirection of the westerly flow, but the key difference from the STR is that blocks are closed anticyclonic feature with trapped air masses. To distinguish these two patterns, we applied two dedicated algorithms, Sousa et al. 2021 for the STR, and Pelli and Hawkins 2003 for blocks. And here we have the answer of our question about which pattern are those Z500 anomaly corresponding. The anticyclonic pattern are associated with the summer region. If we look at the summer climatology, from the top panel, we can notice that the climatological summer frequency of the STRs in the Mediterranean is between 0 to 0.8, meaning that they occur every roughly 1 or 2 days. So they are common feature of the Mediterranean atmospheric circulation, while blocking on the other end, in the bottom panel, has climatological frequency between 0.02. So they are extremely rare in this region during summer. Then, if we look to the composite map of the STR frequency anomaly during our macroevents onset, so we did basically composite of the STR frequency of the 5 days prior our peak, because this is the period that we are analyzing, this map show a significant increase above the marine heatwave affected region. So the rate of the occurrences of this pattern rises to approximately 1 per day, meaning a persistent ridges. The pattern shift after eastwards from the Western Mediterranean, the Central Mediterranean, and the Eastern Mediterranean, aligning. So this pattern are aligned to the marine heatwave intensity. These results are consistent as statistical significant across all the three subbasins. But now, going a step forward, it's not just about the STRs, but it's about STRs that concurs with anomalously weak winds. The map on the top shows the wind speed anomaly composite during our marine heat waves onset, and we can notice that we have reduction of from 2 to 4 meters per second of the wind in the affected area. For example, in the Western Mediterranean, we have a shutdown, basically, or a weakening of the Mistral. Here, they are the strong northwesterly over the Gulf of Lion. And then we have, for example, here, the weakening of the Etesian, that are the typical winds that are particularly strong in the Aegean Sea. To quantify the strength of this combined effect, we calculate the likelihood ratio. So basically, we calculated how much more likely is a marine heat wave under a given atmospheric condition compared to the background probability. And the table tells a very clear story. When persistent STR and negative winds anomalies co-occur, so here, the likelihood ratio rises to 4.3, 4.2, 4.8 for the for our three region. So this means that the marine heat waves are 4 to 5 times more likely when both conditions are simultaneously present. But crucially, neither the STR alone nor the wind reduction alone significantly rise the marine heat wave probability. Indeed, the ratio the likelihood ratio is actually below 1. Okay, so now we go a step further in the local condition. Now we can take a look to the physical mechanism that connect the weaker winds to the SST increase. So the link is the evaporative cooling. So weaker winds suppress evaporation at the sea surface, which reduced the latent heat loss from the ocean to the atmosphere, because those are anomaly. And so the latent heat, so the ocean is losing less heat, let's say in this way. So basically the heat that would be normally be released stay in the ocean and is not going to the atmosphere. So the map is showing the ERA 5 latent heat anomaly composite for the Western Mediterranean. And we can see that we have positive anomaly up to 50 watt per meter square. So the ocean, as I said before, is retaining heat. Then with the scatter plot, we quantify the daily relationship between the wind speed anomaly and the latent heat anomaly. And we have a correlation of 0.7, so a negative correlation, sorry, of minus 0.7 for the Western Med. And this is coherent for all the cluster. We have a strong correlation and we have this latent heat. So this is a confirmation of the this physical mechanism. These slides bring everything together in order to be more quantitative. Panel A is showed the observed SST tendency during the onset of the marine heat waves. And panel B is showing the equivalent SST tendency derived from the total air-sea heat fluxes alone. We can notice that though these two patterns are similar and with the magnitude are quite identical, meaning that the air-sea fluxes explain the SST tendency. Then from the panel C, from panel F, we break down the contribution of the individual flux component, and we can notice that the latent heat is the dominant, accounting for over 80% of the flux-related SST tendency. So basically, we demonstrate that the latent heat is the RC fluxes that is responsible for the SST tendency, so the changing in the temperature. The remaining 30% is probably due to non-atmospheric process, such as ocean advection, missing, and so on. Okay, so now, since I said a lot of things, I will summarize. This slide summarize a bit the chain visually. So what we identify is that persistent subtropical ridges that concurs with actually is in this way. Persistent subtropical ridges leads to positive Z500 anomalies that lead to weakening of wind or the prevailing wind system, which causes a reduction of the latent heat loss through suppressing evaporation. This increase increase the SST and is bringing to a marine heat wave. This relationship is the K mechanism that we have identified in our paper. Okay, so this is the conclusion. To summarize, we have identified the main synoptic scale driver of summer marine heat waves across the Mediterranean. That are the combined effect of persistent STR with weakening of the prevailing wind system. And this has some implication, and I wrote like 2 implications here. So first, the STR and the wind reduction pattern can be used as an indicator for marine heat waves occurrences. And they can be integrated, for example, in machine learning based forecasting system, and or they can use with a predictability windows of approximately 10 days. And then the second implication, and now we have a new open question that we have to tackle, and this is what triggered this persistent of STR during the summer. Here you have the title and the article, and this is all. Thank you very much.